Today I am going to tell you about the k-variable model. Before going into the k-variable model, at first I want to tell you about the two-variable model. Two-variable model in econometrics is a model where we have only two variables. One is the independent variable and another one is the dependent variable. So a two-variable model can be written in the form of yi equals to alpha plus beta xi plus the error term, which is represented as ui. Now here this xi is the independent variable and yi is the dependent variable, and there are only two variables in the model. That's why it is known as two variable model, and we have to estimate the parameters alpha and beta from the model. Now if suppose there are k number of variables in the model, then that is supposed to be called as k variable model. That can be written as yi equals to beta 0 plus beta 1 x 1i plus beta 2 x 2i, and it goes up to beta k minus 1 into x k minus 1 I. So basically there are total k minus 1 independent variables, and in the model there is a dependent variable also. So totally there are k minus 1 plus k minus 1 is the number of independent variable, and 1 we have the dependent variable yi. So there are total k number of variables in the model, and this is basically a k variable model. You may write it in a more simplified way, like you may write it as, sorry for the interruption, you may write it as yi equals to beta 0 plus beta 1 x 1i plus beta 2 x 2i, and it goes up like that, it continues up to like that, and then in the last you may write beta k into x ki. So basically this is nothing but it is the number of variables in the model are totally k is the number of independent variables in the model, and there is a dependent variable also. So there are total k plus 1 variables in the model. This is k plus 1 variable model. You may call it as k regressor model. K regressor model means there are total k number of regressors in the model. That's why it is termed as k regressor model also. Now if I want to form this model in the approach in the suppose if I want to form this model, if I want to form an equation of yi equals to beta 0 plus beta 1 x 1i plus x beta 2 x 2i, and there are other variables, and it continues up to k beta k x ki plus the error term, which is obviously there. Now basically if I suppose or if I assume that y is the demand of potato, so the dependent variable is basically nothing but it is the demand of potato, and there are some other variables like x1i, which is the first independent variable. It is nothing but the price of the potato, price of potato. Similarly x2i is the price of a relative commodity of the potato, or it is basically the price of onion. So the price of onion can also affect the demand of the potato. And the last one I am talking about x. There are other multiple variables in the model, but I am only talking about xki, which is the last variable of the model. That is nothing but production of potato in that particular year, production of potato. So these are the variables that we have in the model. Now basically in the first day, suppose I am sending my researcher to collect the data from the market. So when he reaches the market on the first day, the data that he receives is basically like this. So it is y1, that means the price of the potato on the first day, the demand of the potato on the first day, equals to beta 0 plus beta 1 plus and now beta 1 x11. What is x11? It is the demand of it is the price of the potato on the first day. Always remember that when I am writing x11, this first one is denoting the number of observation or the ranking of the observation, okay, and the second one is denoting the number of equation. If it is written like this x12, then it is supposed to be the first observation of the second equation, okay. If it is written as x23, then it is the second observation of the third equation, okay. So basically beta 1 x11 means x11 here means the price of the potato on the first day, and beta 2 x21, it is basically the price of the onion on the first day, and last one is beta k x ki. There are some other variables which we haven't included, I mean we haven't mentioned in the equation. Beta k x ki, which is not xki is xk1, xk1. So it is nothing but the production of potato in that particular year or in the first year, okay, and plus ui, or you may just give it u1 also, okay. So this is the case of the data finding. I mean the researcher that I have sent in the market, he found all of this data from the first day. From the second day also he will find some data that will be represented as y2. Here y2 is nothing but the demand of potato on the second day, and the equation can be written as beta 0 plus beta 1. x11 will not be written here, it will be written here. It is the second equation, obviously. From the second day we have the second equation, so it will be because of the equation, this is representing the equation, this is representing the equation, this is representing the equation, okay. So basically on the second day it is the second equation representing the second equation, but it is the first observation, so it will be written as x12, okay. This one is representing the first observation of the second day, and this 2 is representing the equation number, okay. Now beta 1 x12 plus beta 2 x12 and then beta 2 x22. This x12 is nothing but the price of the potato on the second day. This x22 is nothing but the price of the onion on the second day. At last this beta k x k2. So this xk2 denoting that price of the potato, production of the potato on the second day that we have obtained. So now if I want to form what will be the equation on the nth day, or what will be the data finding on the nth day. So for finding the data finding on the nth day, we have this kind of equation, that is yn equals to beta 0 plus beta 1 x1n plus beta 2 x2n. So basically this n is denoting the number of equation, it is the nth equation, the data found from the nth day, so it is the nth equation, and this one is the first observation, second observation of the nth day, and at last the last observation can be written as beta k x kn, okay, and plus the error term, that is un, okay. It is also suppose the error term, okay. Now clear. Now if I go to on the matrix approach, if I want to form this in the matrix approach, then we have basically a matrix of the dependent variables y, that is y1 y2 y3, and it continues up to yn. So basically how many rows are there in this matrix? There are n number of rows, and there is only one column in this matrix, so it will be the dimension of the matrix will be n cross 1. Similarly, if I want to, as you can see, the entire model is written on the if I want to write it in the matrix form, then the entire model will be formulated by the dependent variable, the parameters, the independent variables, that is the x11, x21 and all that, and the error terms obviously. So at first I have to include the independent variables. So the independent variables, the matrix of the independent variables will be in the form that at first I have to give 1 1 1 in the first column. It is because of the parameters that we are going to have in the equation. If I after writing, if after I complete writing this matrix form, then you will be able to understand it clearly that how are we getting the equations from the matrix. Now, what was basically the first equation? The first equation was having the independent variables x11, x21, xk1. So we have to just take the independent variables x11, x21 and then xk1. Similarly, what was the equation in the second day? In the second day we have the independent variables x12, x22 and xk2. So x12, x22 and then xk2. Okay, so it goes up like that. I am not going. The last equation on the nth day was basically showing us that we have the independent variables x1n, x2n and xkn. So let me write that x1n, x2n and xkn. Okay, so I hope this is clear. Now, what was our matrix of parameters? This was basically our matrix of the independent variables, and this matrix has the dimension. It has total rows. It has total almost k plus 1 rows, because k was supposed to be the rows if there was only this amount of or this number of variables, but it also has this 1 1 1 1 along with it. So there are total almost if I talk about rows, then there are total n number of rows. Okay, because this on is continuing up to n, and number of column in this matrix is there are total k plus 1 column, because k was the number of variable, k was the number of k was supposed to be the number of columns, but there is an additional column of 1 consisting of 1, so we have k plus 1 as the number of columns. So this was our dimension of the matrix, that is n cross k plus 1. It is supposed to be given with by a bar or represented by a bar. Now the matrix of the parameters will be shown as beta 0, beta 1 and it will continue up to beta k. It also has the dimension of, it has how many rows do we have in this matrix? We have almost k plus 1 rows, and the number of columns that we have in this matrix is nothing but only 1. So the dimension will be k plus 1 cross 1, and we have to add it with the error terms, which are u1, u2 and it continues up to un. Okay, and this matrix is completing here, and the dimension of this matrix, there are total n number of rows, but columns are only 1, so it will be n cross 1. I hope you have obtained the value. Now if I just multiply the first row, okay, let me change the color. If I just multiply this first row of this independent variable, the matrix of independent variable, with the with this row of parameters, and then add it with the errors, then what will I obtain? So at first this 1 will be multiplied with beta 0. If I write that equation, so y1 will be taken from here, and y1 will be equal to this 1 will be multiplied with beta 0, so you will get only beta 0. Right now this x11 will be multiplied with beta 1, and we have an addition of it. beta 1 x 1 on. I hope you all know the basic rules of multiplication of matrix, and then this x21 will be multiplied with beta 2, which is not written here but it was there. So x21 is multiplied with beta 2 x21 plus the last one is beta k1, and it will be multiplied with beta x k1, and it will be multiplied with beta k. So we will have x k1 beta k, so it will be beta k x k1. Okay, and the last one is the very important. We have only the u1 plus u1, so plus u1. So basically this was our first equation, and we have also obtained this equation from the beginning on the first day. If you compare it with the equation of the first day, then it was just as same as it was here. Beta 0 plus beta 1 x11 plus beta 2 x21 plus beta k xk1 plus u1. So we have actually given, or we have actually proved that how can we write it in the matrix approach and still conclude with the same result as we have obtained from the data collection. Okay, now leading to the next part. So I feel I have written the dimensions of all the matrix. Yes, I have covered all the dimensions of all the matrix. Now this matrix can be written in the form of this is y matrix, that is our matrix of dependent variables. This is x matrix, that is the matrix of our independent variable. This is our parameter matrix, that is the matrix of our parameters, and this is the error term. So I may write this matrix as y, this matrix as x, this matrix as beta, and this matrix as u. So basically this matrix we may write it as let me clear it. We may write it as y equals to x beta plus u. Here this y is consisting of, y is not a variable, it is a vector here, or you may say it is a matrix. It is basically a vector or matrix which is consisting all the values of the dependent variables. This x is basically not a variable, it is a vector of all the independent variables. Beta is not a variable, it is a vector of all the parameters. U is not a variable, u is the vector of all the error terms. So basically this y, the y that is represented here is nothing but this entire matrix. Okay, this x represented here was nothing but this entire matrix, this beta is entire matrix, and this u is also this entire matrix. So now if I go to the next part, if I want to, I hope you have some basic idea about the two variable model. In the two variable model, we write the equation as y equals to alpha plus beta xi plus ui. Okay, now whenever we estimate this equation, this estimation or estimated or regression line of the equation, the regression line of the equation is written as y hat equals to alpha hat plus beta hat xi. Here this beta hat and alpha hat are the estimated values of the alpha and beta, estimators of the alpha and beta. So the error term is not present here because this is basically equation of the line, and equation of the line does not include any error term. Error terms are the points which are not lying on the trend line or lying on the equation, but the equation will not have those error terms, right? Or the line will not have those error terms. The points are above or below the line. If I show it in by graphical method, this is, suppose this is the line, and it is the equation of the line is nothing but y hat equals to alpha hat plus beta hat. Let me clean it a little bit. Yes, alpha hat plus beta hat xi. Okay, now this is the equation, and the error terms are nothing but the error terms are above and below the regression line, but it will not come on the equation of the, it will not be included in the equation of the regression line. Okay, that's why this equation was in the population regression function, but it is not on the sample regression line or the prediction line that we have obtained from the population or the data set or the sample. Now, so basically if I want to estimate or if I want to do the same thing, or if I want to estimate the sample regression form, or if I want to estimate the equation from this entire model y equals to x beta plus u, then how can I do it? So for doing that, I may write it as y hat equals to x beta hat. Okay, here y hat is the estimated vector of y. That means y hat is basically the estimated values of y hat is basically the vector of estimated values of the dependent variables. Beta hat is nothing but the estimator of the beta. That means it is nothing but the estimated parameters of the beta. I mean it is the vector of estimated parameters of beta, and x is the value, or x is the independent variable, vector of the independent variables. U will not be present because it is the equation. It is not the equation of trained line anymore, it is the equation of trained plane, because it is not of two dimensional anymore, it has multiple dimensions now. Here it was only of two dimensions, that's why it was a trained line, but now it has multiple dimensions, so it is basically a trained plane. Okay, so that is the equation that we have obtained. At first we have obtained that y equals to x beta plus u. It is nothing but y is the vector of the dependent and vector of the values of dependent variable, x is the vector of the values of independent variable, beta is the vector of the values of parameters, u is the vector of the values of the error term. If we estimate this equation, then our estimated equation becomes, from this model or from this population regression model, our estimated equation becomes y hat equals to x beta hat. Okay, now leading to the next part, what are the assumptions? What are the assumptions of the OLS technique or CLS technique? Okay, what are the assumptions of ordinary least square method techniques? So the first assumption is there are n observations in the model, and if there are n observations in the model, then there are n linear equations. Okay, there are n linear equations, otherwise we won't be able to solve the entire values of the parameter. Suppose we have only one equation, y equals to x plus 5. Now from this equation you won't be there are two variables in the equation, right? But from these two variables, how can you find out the values? I mean, there are two variables and there is only one equation. So from just two variables and one equation, how can anyone find out the value of the two variables? So for finding out the value of two variables, you need two equations, at least you need two equations, right? So x equals to suppose 2y plus 3. Now from these two equations you may find out the value of two variables. So that is the first assumption, is there is if there are n observations, then there are n linear equations, otherwise you won't be able to find out the value of the parameters. What is the second observation? The second observation that x is non-stochastic, that means x is fixed. Okay, I am not going to elaborate this assumption much, because this is a very much this is very basic. This is from the concept of two variable model also, so I am not going to, it was also in the assumption of two variable model, so I am not going to elaborate it. X is basically non-stochastic or fixed. Number 3 is that there are total, how many parameters are there in the model? Beta 0, beta 1, and it continues up to beta k. Okay, so there are total k plus 1 parameters, but there was another parameter that was also in the model, that is the value of sigma u square, which is the value of the error variance. So the error that we have included in our model, it has a variance, and the value of the variance of the error term is basically sigma u square. It is also a parameter. So there are total k number of parameters, this beta 0, and there are k parameters. So it has there are total k number of parameters, and beta 0 is also also a parameter. So there are k plus 1 number of parameters, and sigma u square is also another parameter. So there are total k plus 2 number of parameters in the model. Okay, now what is our this is our third assumption. Now heading to our fourth assumption. What is our fourth assumption? Basically our fourth assumption is that expectation of u is basically, if it was a two variable model, then we may have written that expectation of ui equals to 0. That means the zero conditional mean of the error term. That means the error term has zero expectation. if we do the expectation of error term, then we will have 0 as our value. But expectation of u, here this u is not a error term only, it is the vector of the error terms. U is nothing but u1, u2, and it goes up to un. So it is the vector of error term, right? So expectation of u is basically null here. It is not like this, it is not like a single 0, it is null. That means it is like 0 0 0 0 and it goes up like that. Okay, so I hope this is clear. This is the fourth assumption. And if we go to the fifth assumption, so our fifth assumption tells us that expectation of u dash is basically sigma u square I. This is also the spherical property of the k variable model. If this was not supposed to be sigma u square I, then we may have headed to the non-spherical model. That is a different concept although, but in the CLRN or in the CLRS technique or OLS technique, we assume that expectation of u hat is nothing but sigma u square I. How can we derive it? This is also called the dispersion matrix of the error term. This is also called the dispersion matrix of the error term, and let us see this dispersion matrix of u. So u here is nothing but a vector of the error terms. Okay, so so for finding out the dispersion matrix, we have to find out the expectation of u dash. Okay, this u and u dash. Now it can be written as, now what is u? U is basically vector of the error term. So u is u1, u2 and un. And what is u dash? U dash is basically nothing but the transpose of the u. So it will be written as u1, u2 and it goes up to un. Now if we multiply this both, what will we get? We are going to get a matrix. Let me write that matrix here. It will be a very big matrix. So at first what will happen? At first this u1 will be multiplied with u1. So we will get u1 square. And obviously all of these things are within expectation. So let me clear that also. Sorry. Now the first term that we will get is u1 and u1 multiplied, we are getting u1 square. The second term that we are getting is u1 multiplied with u2 and we are getting u1 u2. And it goes up like that, and the last term we are getting that on the first row. The last term that we are getting on the first row is u1 multiplying with un. So we are getting u1 un. I am not calculating the other rows. The last row I will calculate directly, or let me calculate the second row also. For the second row, u2 will be multiplied with u1 at first. So we will get u2 u1. Then we will have this u2 multiplied with u2, so we are getting u2 square, and at the last we are getting u2 un. Now let me calculate this for the last term, that is un multiplied with u1, we are getting un u1, then we are getting un u2, and it goes up like that, and the last term that we are getting is un square, because this is the last term that we are getting, un multiplied with this un, so we are getting un square. As you can see, if we take the expectation now, if we put this expectation within the matrix, then what will we get? We will get expectation of u1 square, expectation of u1 u2, expectation of u1 un, and here we have expectation of u2 u1. Okay, and then expectation of u2 square, and it goes up as to expectation of u2 un. Then just for the last matrix, that is expectation of un u1, expectation of un u2, and it goes up like expectation of un square. So basically what we are having here, as you can see, these are nothing but 0, because the error terms are obviously not correlated to each other, so their expectation will be 0 because they don't have any correlation with each other. So this, all of these terms will be nothing but 0, converted into 0. But these diagonal terms, expectation of u1 square, expectation of u2 square, expectation of un square, we all know that the error terms follow an assumption, that is the homoscedasticity assumption. That means their variance of the error terms. How can we calculate the variance of error term? The variance of error term is nothing but variance of ui. Now variance can be calculated as expectation of ui minus expectation of ui whole square. This is nothing but 0 because of the 0 conditional mean or 0 expectation of the error term. So we have expectation of ui square as the variance of ui, and this is considered as nothing but constant. In the CLRM assumption it is considered as constant, so we take it as constant as sigma u square. So all of these terms are nothing but expectation of u1 square, u2 square, these are constant, right? Due to homoscedasticity assumption, all of these are same and constant. So we may put sigma u square in place of all of these diagonal terms and 0 in place of all of these remaining terms. So our new matrix will look like this. That will be 0, in the diagonal terms we have the constant value sigma u square, but in the remaining terms we have 0 only. Zero, sigma u square, 0, 0, 0, 0, and sigma u square. So the diagonal terms are 0, are sigma u square, but the other terms are nothing but 0. So we may take sigma u square common out of this matrix. So our matrix will look like this. After taking the sigma u square common out of this matrix, the diagonal terms are now converted into 1, but the remaining terms are nothing but 0 still. Okay. Now heading to the matrix, this is nothing but an identity matrix, because the diagonal terms are 1 and the remaining terms are 0. So this is nothing but an identity matrix. So we may write it as sigma u square into I denoting an identity matrix, and this I has a dimension of n cross n. Okay. So now basically we have proved that the dispersion matrix, that is the expectation dispersion matrix of u, that is nothing but the expectation of u and u dash, is nothing but sigma u square I. Okay, so this is a spherical property also, and this is the fifth assumption also. Now heading to the sixth assumption, it tells us that there is no relationship between the explanatory variables. The explanatory variables, suppose xi and xj, there is no relationship. That means the correlation between xi and xj equals to 0. So that is the assumption of multicollinearity, that there is no relationship between the explanatory variables. It can be also written as correlation is nothing but, we all know that correlation is nothing but covariance between x and I and xj. So and divided by sigma of xi. Here it might be some problem with the link, sigma xi and sigma xj. So basically I hope, yeah. Okay, now this covariance is supposed to be 0, for this correlation to be 0. This covariance, the numerator part, is also supposed to be 0. So we may also write it that covariance of xi xj equals to 0. It doesn't matter whether you write covariance of xi equals to xi xj equals to 0, or you may write correlation of xi xj equals to 0. Both of this implies that there is no relationship between the independent variables, and there is perfect multicollinearity. There is no multicollinearity. That means there is no relationship between the independent variables. And the last assumption is that the seventh assumption probably, it tells us that there is no relationship between the explanatory variable and the random error part. That means the correlation between the independent variable or explanatory variable and the error term is nothing but 0. You may write it also as covariance of x and u equals to 0. I have shown it how the covariance and correlation are basically the same things in case of they are becoming 0. Okay. Now if I want to find out the calculation of the least square method. How can we find out the value of the parameters in the regression equation? I mean, as I have said also, that in the two variable model which was written here, let me show you. In the two variable model, our objective was to find out this alpha hat and beta hat. But in a k variable model, our objective will be to find out the value of these parameters, or the value of the vector of which is consisting the parameters. So our objective will be to find out the vector which will give us the value of the parameter beta 0, beta 1, and goes up to beta k. So how to find out this vector, or how to find out this vector which are consisting the values of the parameter? I will show it in the next video.